All right, so there's our rate law that we came up with from that equation. Whoops. Again, it's just what we talked about. That's the rate law. Now we see a real rate law for an actual reaction. Some terms that were listed on that last slide, but I've just got kind of expressed as full sentences here. The exponents are what we call order. So if I said, what's the order of that reaction for NH4, you would have said first order because there's an understood exponent of 1 after, or we actually even wrote the 1. It's first order for NO2 as well because its exponent was a 1. But if I said, what's the overall order for that reaction, I think I would have had to say that one was second order overall because 1 plus 1 is 2. So the overall order for the reaction is something we talk about from time to time. And it's where you add up the exponents. Next, we're going to look at the example on the back, which is a more interesting data table compared to the last one because we'll see something get squared instead of just first order for both of those. And it's also, all you really need are 3 reactions, or 3 experiments on a data table. That last one had a lot of extra options for us. Does anybody need more time here? Okay. So an individual reactance order is its own exponent that we got from our table. And then if I say, what's the overall order for a reaction, you add up the exponents. And notice, of course, 1s are frequently going to be understood. I wanted to write the 1 on there to get in the habit of having one. But a lot of times, like we see in the example, the way it's written there, the 1 will just be understood if it's first order. Anybody need more time now? Okay. All right, so here we've got a different reaction. So it's going to have a different rate law. It's going to have a different rate constant. But it's still going to follow that same pattern. Rate equals K, blah, blah, blah to the X times blah, blah, blah to the Y. We can go ahead and get that template down for this reaction since we know what it generally should look like. So I'll go ahead and start with that. Rate equals K. That's what a rate law always starts with. And then what's going to go in the first brackets for this rate law? Even though I don't know the numbers yet. Mackenzie, what would go in the first set of brackets here? NO. YES. And then in the second set of brackets, again, we'll leave a little space here because we're probably going to have an exponent. Even if it's a 1, we can put it. Pavitra, what's going to go in the second set of brackets? H2. And then we expect to put something there. Again, you don't have to put a 1 there, but if it is a 1, we'll just put it there to emphasize it. Now, to find those exponents, we're going to our table. So NO comes first, so I want to find 2 reactions, 2 experiment numbers, where NO changes, but H2 is held constant. Will, what are 2 reactions that you see, 2 experiment numbers, where NO changes but H2 is held constant? So focus on H2 at first then. Where is H2 held constant? 1 and 3, yeah. Yeah, so they separated them for that one, huh? So 1 and 3, last time they were nice and neat in order. This time, because there's only 3 reactions shown, 3 experiments shown, if we look at 1 and 3 at first, we can see that NO doubles while H2 is held steady there. I won't mark it out because we'll use it later on. H2 is held steady, So I can focus just on the effect of NO. It goes from 0.1 to 0.2. So just in general, Piper, how did NO change? Did it double, triple, quadruple?
It doubled.
It doubled. So it increased by a factor of 2, doubled. And then if I look at this, I'm going to see the rates change as well. Those numbers to me are kind of complicated and hard to deal with, so I might pull out a calculator and I might do the big one over the small one. 4.92 times 10 to the negative 3. Over, and then I better use parentheses for that bottom part, unless I want to take it out of scientific notation or if I have a good calculator and I know for sure what I'm doing. You could also let the 10 to the negative 3's cancel. All right, when you divide that and get the change there, Joseph, how did the rates change on that one?
It's like, it says 3.48, so like between 3.
You might have switched two numbers because I'm getting exactly 4. You might have swapped the 2 and the 9 or something like that when you typed it in.
I did, yeah.
Okay, so we'll get exactly 4 with those numbers there, so that's even better. But if you ever got 3.5, I would redo it because these are always going to be really close to nice whole numbers. So that went up by a factor of 4. So if the concentration of NO doubles, but the rate quadruples, what should our exponent be for this one, Sydney? Good job. So this is going to be an exponent of a 2 for the NO. All right, so keep that in mind. If you ever see a concentration double, but the rate quadruples, that relationship is supposed to be like 2 squared equals 4. These can be square relationships in that way. That's why that occurs that way. So we have to square the NO, and this is going to be second order for NO in this reaction. Now, again, you've got all that stuff in pencil. I'm just going to erase all this junk and focus on 2 experiments where H2 changes, but NO stays the same. Shelby, where does NO stay the same? What are 2 experiments where NO stays the same? 1 and 2. Yeah, those were first 2 there. So let's look at just experiments 1 and 2 now. All right, how does H2 change between those experiments, MK? It doubles. Now this one, you might want to pull out a calculator, maybe not. You might be able to see that. If it goes from 1.23 times 10 to the negative 3rd and it goes up to 2.46 times 10 to the negative 3rd, and it's kind of neat. If the scientific notation stays the same, you can cancel those if you want, and then it's easy to see that relationship. That's what I did on the last one. So Carter, if we go from 1.23 to 2.46, what's the effect there? It also doubled this time, so it just doubled. So if you double the concentration and you double the rate, Vivi, what's the exponent that we're going to put this time? Yeah, it's just first order with respect to H2. So this reaction is, and again, I'll erase those little dotted lines so it's easier to see the numbers. This reaction is second order with respect to NO, and it's first order with respect to H2. This question isn't on the sheet, but what's the overall order for this reaction, Kira? How do you find overall order again? Yeah, good. The overall order, if I said, what's the overall order? Good job. It's third order overall. This reaction is third order overall. It's not on here, but it's something that you'll see on the assignment and everything. So find the value of the rate constant. We're going to do the same thing we did before. So from this point on, it's very similar to what we did last time, except for the unit. The unit on the rate constant will change. So this time we're going to Pick a reaction. I like reaction number 1. That's just what I go with. 1.23 times 10 to the negative third. You know what? I don't like scientific notation. I'm just going to take that out of scientific notation as it gets started. So I'll call that 0.00123 molar per second equals K times, I'm going to go with 0.1 for NO. I'm looking at reaction 1, but if you want to try it with reaction 2 or reaction 3, you'll get the same answer. Reaction 1 is extra easy this time because it's all 0.1s. Okay, let's solve that for K. I'll do the right side first. Again, I'll do that on the board down below. Point 1 squared times 0.1. 0.001. So it looks like we're getting 1.23 for our answer here. Now this one was third order overall, and it turns out when reactions are third order overall, their unit for their rate constant is a little bit different than last time. It's actually molar to the negative 2 times seconds to the negative 1. Again, the whole point of that is to make sure that molarity squared times molar times something else gives us our final rate unit in molar per second. So the rate constant has funky units. Whole purpose of those is to make sure the other units work out. And now we get to kind of see how that works here. We can find a particular rate if we just use that equation. Rate equals K. We just figured out that K is 1.23 molar negative 2 seconds negative 1 times 2 squared, 2 molar squared, times 2.5 molar. Just multiply those three numbers times each other, making sure that I square the two. 1.23 times 2 squared times 2.5. I'm getting 12. I didn't have to put 1.23 times 2. 12.3. That's a 1s and 2s and 3s here. So it's going to be about 12.3 with sig figs. You could even take it to 12. I just noticed that those concentrations in the chart just had 2 sig figs. So 12, and then the unit for rate overall, again, it's just molar per second. The actual rate is how is the molarity changing every second. So as this particular reaction proceeds, the rate is changing by 12 molar, or the rate is 12 molar per second. All right, so the big difference in that one that I wanted you to see was the NO, how it doubled and the rate quadrupled, so we had to square its exponent, and it was second order for that one. Okay, number 14.26 is actually going to be even easier because they want you to write a rate law, but they give it to us in sentence form. And that's the last thing that I wanted to finish with today was this example problem here. Looks like the same reaction we were looking at before, but we can actually, sometimes the question is going to, instead of giving us a data table, they're going to make it even easier for us. And they're going to give us a sentence, and we just have to translate that sentence into a rate law. It says, considering the following reaction, the rate law for this reaction is first order in H2 and second order in NO. Write the rate law. So we're looking at those words like order. First order in H2 means that when I write my rate law, it's still going to look at the same way as any other rate law at first. It's always rate equals K, blah, blah, blah. That's a rate law. Rate equals K, blah, blah, blah. If it's first order for H2, they're telling me the exponent for H2 is a 1. If it's second order for NO, they're telling me the exponent for NO is a 2. It doesn't. So I know that, you're noticing last time we did it NO first because it's the first one. For the rate law, it doesn't matter. I'll just go in the order they told me in the sentence, but you could switch it. As long as the 2 goes with the NO, that's the most important thing there. And then from that point on, they tell us the rate constant for the reaction. They must have changed the temperature compared to last time because now this rate constant is really different. So in part B, they want us to find the rate because they're telling us the rate constant. So this is even easier. Instead of looking at the chart and stuff, they're telling us all the answers and what to do to solve this one. So now they're saying find the rate if you know the rate constant is 6 times 10 to the 4th all right, it's got that weird unit again. When NO is 0.35 and H2 is 0.015. So make sure we plug these in the right spots here. H2 is 0.015, NO is 0.035. They keep switching the order around on us. And then we would just, like before, you would just multiply those 3 numbers times each other and make sure we square the 0.035 first for order of operations. All right. The last thing I want to do is to go over the units for the rate constant. I don't think I have that on here. Depending on the overall order. So if a reaction is second order overall, I'm going to skip a line because I only have a spot for first order overall. But we saw second order overall. We add up the exponents, and add up to 2. The unit for K was molar -1 seconds -1. When it was third order overall, like this example that we've got on the screen right now, it's molar -2 seconds -1. If you ever have a reaction that's just first order overall, -2, -1, that takes us to 0. Anything to the 0 power is really just itself. So it turns out the unit, if it's first order overall, is just seconds -1. And anything to the 0 power is 1. Molar to the -1 is there. Molar to the 0 is actually just 1. Anything to the 0 power is 1. So if it's first order overall, the unit for K is just seconds -1. So your assignment has a lot of these tables, just like we were looking at, where you'll focus on one reactant at a time, see how it changes, use that to write a rate law, and then plug in some values for it. And then there's a couple that are sentence form like that are even easier because they did the work for you when they're in sentence form. You just have to read the sentence and put the exponents in the right place. The homework assignment I want you to do for tonight. Yeah, thank you. I need to do that for chapter 14 now, huh? I'll get on that right now.